Okay, we were talking about the solar eclipse from Monday, and I was mentioning that, yes, it was mentioned there's several articles floating around about, there was one that was in Vox Media that was something like the solar eclipse is a critical test for the US power grid, and just kind of goes to show how maybe sometimes the interview and you get quoted in one way and it gets made a little bit more dramatic than you really intended. I don't know that it was really a critical test for the power grid, but did definitely have a much more significant effect than the solar eclipse had that we experienced in 2017. The amount of solar generation between 2017 and 2024 has increased very, very significantly. And to give you a taste of that, I want to share something that was created by my colleague Tom Overby at Texas A&M. And what he did for this was we've got information about all of the solar generation in the US and the geographic location of it. That's all public data. And then we have access, we can calculate the solar irradiance in a normal day based on the sunrise and sunset and all that sort of thing. And then overlay that with the eclipse reduction in solar irradiance. And then you can also overlay on top of that cloud coverage. Of course, you don't know the cloud coverage until the day actually occurs, but for illustration purposes, we can show what it looked like if you used an equivalent day from a previous year. So that's what this, I got two videos. One of them, there was actually two eclipses in the last year, which you guys may know. And one of them is October 14th, 2023. So here's the video for that. I'll just play both of these videos here really quickly. Again, this is by my colleague, Tom Overby. Hopefully this will play. Created using PowerWorld Simulator. These white circles, oh, wow, you can't see anything. Hold on. When has that been gone this whole time?
No, just maybe switch that.
All right, hold on just a second. Let me get the projector going here again. Okay, how about that? There we go. Back up here. Okay, start the video over. What this is going to show, again, there's going to be little white circles that represent the solar plants at a utility scale. And then the sort of darker blue is lower solar, very little solar. Red would be the highest level. So this would be the sun rising in the east, of course, and the solar goes up the east coast and then kind of throughout the country continues to rise. But then you'll see the solar eclipse come across. This is the October one. I guess for October it came this way. And you can see, notice the Texas solar going down there during the period of the eclipse, and then coming back up as the day continues. Kind of interesting. It's going to show it again with a cloud cover. Again, this is not the cloud cover of the actual day, but the cloud cover of a comparable previous day. And it would need to be updated after the eclipse with the actual cloud coverage data to see what's going on. So let's see, here it is. This is basically assuming the cloud cover from October 14th, 2022. And you can see the cloud cover data where there's going to be very little solar there. And you can see that it's much lower where there's cloud cover. And then you can see the eclipse coming again from the northwest with the region of totality coming down across Texas there and reducing the solar output. You know, people ask, you know, in this, here, I'll go ahead and play the one from just this past week while I'm talking, but people kind of ask me, you know, what is, you know, is this really a significant event for the power grid? And the answer is it definitely is a significant reduction in solar output. It also has an impact on the temperature and therefore an impact on the load. You know, when it comes to like how predictable things are that are going to impact the power system, there's almost nothing as predictable as a solar eclipse. I mean, we know the exact path of a solar eclipse many decades in advance. And so, I mean, you have plenty of time to plan. So it's not like an extreme event where you don't know what's going to happen, and then, you know, it comes on all of a sudden and you got to take into account all the uncertainties and that sort of thing. I mean, we know the exact path in advance. There's the path of the solar eclipse in whatever day it was, April 8th, I believe, 2024. We did have pretty significant cloud coverage in Texas. I did not So College Station's kind of down here. We weren't quite in the path of totality. I just kind of looked out my office window and saw all the students like looking in their glasses up at the sky during the afternoon on Monday. So this is a slightly different color scheme here, but approximately the same idea. This eclipse coming from the south. Friend of mine in Ohio got a pretty clear view of it. Yeah, so yes, you can see the total per state and the total. So each so this is based on EIA 860. So the Energy Information Administration publishes a list of all the generators that are out there, their capacities and so forth. And so this is based on the assumption of these solar irradiance relates to the solar output. And so it's based on kind of an assumption of what output there would be associated with that. So it's not based on measured actual output data. I'm sure that some people will be doing some assessment of that and kind of seeing how the prediction was compared to the reality, just to kind of give you a visual impact of what's actually going to be happening. But if you look at the total US solar in this relatively cloudy day, you can see how much more significant this was than even just a few years ago. So I thought this was interesting, just kind of added this to the beginning of the presentation at the last minute because I thought you guys would think that was kind of cool. Yeah, like I said, I mean, what's really scary in a power system is what you don't know and what's unpredictable and what could be challenging in the future. And, you know, astronomy is one of those areas of science that is pretty accurately predictable, at least in terms of things like solar eclipses. So, you know, from that perspective, I'm not really worried about solar eclipses as likely to cause blackouts anytime soon. Okay, so back to what I was hoping to talk about. I mean, let's see. So on Zoom, you're probably looking at the. So I'm gonna do a duplicate slideshow. That way everybody can probably see both. That's still showing there. Okay, good. So solar eclipse. So I want to just ask a couple questions of the students in the back to get the interactive going a little bit. And you guys are in electrical engineering, and a lot of you are studying power systems. So I want to just back up to a broader question, which is saying, electricity is not found naturally, except in a few very unusual things, lightning, electric eels, a few things like that. And we don't really use electricity directly for any of the energy needs that we have for day-to-day life. We use energy, we use lots of energy, we use it for other things, and we have lots of energy out there in different forms. Why is it that something like 40% of our energy today, in its path from the condition in which it's naturally found to the condition in which it's finally used by human society, is it transmitted electrically? That is, why is it that so much of our energy usage is transmitted electrically today? Why do we use electricity for large scale? I mean, we're talking about large scale energy delivery, big picture. We naturally are going to be talking about electrical engineering. Why is that? What do you think? Yes. Transports quickly. What could be faster than approximately the speed of light? Yeah. Other thoughts?
It's more economical, weighs less than transferring energy.
It weighs less. I never heard it stated quite that way. Yeah, it does. It definitely does. Right? I mean, if you have to transport a fuel in a truck or on a train across a long distance, that takes a lot of energy, and therefore efficiency is part of that, right? So you would lose more energy in transmitting fuel over a long distance. Yeah. So we could transmit large amounts of it over long distances because we can use electrical conductors is kind of the fundamental answer if you ask me, but also because there's very convenient ways of converting power from non-electrical forms to electrical through to generators and then also in other technologies, and then also converting that electric power back to the forms in which humankind wants to use energy, and the amount of energy that when I'm looking from a big picture societal point of view, we have a lot of energy in some form or fashion that we need to use to maintain good human society. And how are we going to get that energy? We've developed a large scale electric power delivery network that's used for most of that, and actually is the share of energy that is going through electrical at some point is getting larger, and therefore that's basically my motivation for wanting to study bulk electric grids. Is this system is integral to modern life. Not only do we use electricity for most power systems, we also use AC electricity. And because I spent so much time on the solar eclipse, I'll not make a big discussion about this, but the reason, which most of you know, that we use primarily AC electricity, alternating current electricity, which means that instead of just having a current or voltage at some steady value, it oscillates up and down many times per second. Why do we do it this way? Basically, if you think about a sinusoidal waveform, if you think back to trigonometry, sinusoids are associated with rotational or circular motion. Circles and sinusoids are connected. Better performance in motors and generators. Motors and generators they like sinusoids. And then the other one is that there's magnetic devices with relatively good efficiency known as magnetic transformers that can be used to step up the voltage and step down. Why do we care about stepping up the voltage and stepping it back down? Because P equals V times I. And if you want a lot of P, you either need a lot of V or you need a lot of I. And we'd rather have a lot of V because I induces losses. And so if we can get a higher V, we can get a lot of P for not a lot of I. Okay, so we have large-scale alternating current electricity, but as a consequence of having large-scale alternating current electricity, we've got to keep things synchronized. It can't be that every voltage is just going up and down at its own frequency, however it wants, willy-nilly. No, it's not possible. They need to be synchronized. And so if I measure the voltage right here and I see how it's going up and down and up and down, and I compare that to San Diego, and I compare that to Vancouver, British Columbia, and I compare it all the way to El Paso, Texas, I'm going to see sinusoids that are going together up and down. And if you look at all the spinning generators, the synchronous machines, they're going to be spinning together at the same speed, same frequency. They have to be keeping in synchronization with one another. There's good reasons, engineering reasons. We've got to use AC. It makes the most sense for what we're doing today. But there's also the implication of needing to keep things synchronized. Why 60 hertz? Why is it that modern power systems, you may know, go up and down 60 times per second? Seems almost like an arbitrary number if you don't know. And so, you have a question?
Visual, isn't it just to follow?
I thought you were telling me I need to hurry up. I'm almost out of time.
Keep talking.
Okay.
Keep talking again.
It is true that there are some clocks that at least historically have operated by counting 0 cycles, but that's not why it's 60 hertz. It turns out it's really just kind of a compromise. There's reasons why you don't want it too much lower, and there's reasons why you don't want it too much higher. The reasons you don't want it lower, one very practical one, is flicker. If these lights were kind of going on and off at 10 hertz, you would be able to notice. Your eyes would, but 60 hertz, they won't notice. LED, it's not really how it works anymore, but certainly with incandescent, that was an issue. Also, the lower the frequency, you have to have larger motors and transformers because you'll get to magnetic saturation faster without it. So lower is good for bigger, lower losses. And then why not higher frequencies? Higher frequencies have higher voltage drops over long distances. If you remember back to AC circuit theory, the impedance Z is equal to J times omega L, right? Omega is that frequency. Higher frequency gives you a higher impedance. So higher frequency, yes, you can make things smaller. You're not going to get into saturation, but you're going to have big voltage drops. And then also, the thing people may not think about is that audible noise is more significant with higher frequencies because human hearing range is kind of the hundreds of hertz up to a few kilohertz. And so, but it turns out that 400 hertz is common in some systems where you really need to worry about weight. But today, most people use 50 or 60 hertz. And people ask me sometimes, well, what's the difference between 50 and 60 hertz? The US Canada are 60 hertz. Europe is 50 hertz. China is 50 hertz. Japan, actually, believe it or not, half of Japan is 50 hertz and half of Japan is 60 hertz. What's the difference? I think about it as like the difference between driving on the left-hand side of the road and the right-hand side of the road. It really doesn't matter, but it's really important that everybody does it the same. It's kind of 50 or 60 is fine, but if you connect up, you got to be doing the same thing. So in the US, we use 60 hertz. And here's a map, which you probably have seen before, of the main interconnects in the US. I chose the cities I picked earlier very carefully. Here in Utah, you're connected in with, like I said, San Diego, Vancouver, El Paso, Texas, and the far west is also on the western interconnect. But there are 4 main interconnects in the US and Canada, and some smaller grids in places like Alaska and Hawaii as well. And I say that these are synchronized AC grids, and they're independent of one another, almost independent. And I say almost very intentionally because there are some connections between these grids. The only way to connect 2 AC grids that are not synchronized with each other is through back-to-back power electronic based converters, where you take the AC, use power electronics to convert it to DC, convert it back to AC. So people talk about Texas having an independent power grid, and it does, with a little asterisk, in that there are 4 DC ties from ERCOT to other grids, 2 to the Eastern Interconnect and 2 to the Mexican grid. And so there's 2 places along the border where there's a connection, something around 800 megawatts or less of transfer capability between ERCOT and the east, and there's quite a few along the east-west boundary as well. Things that you may not know is that east and west were actually connected very briefly in the 1970s, and the problem with connecting them back then is that essentially nobody lives there in eastern Colorado, western Nebraska, and all of that, and so there's very little load along that line, and so it was a very long transmission distance. And there were oscillation problems where the east and the west were kind of fighting each other, electrically speaking, and so they decided to break it apart. And I think that there's strong potential that they may connect back up again in the next decade. Part of the motivation for that would be all the wind that is being built in the west. If you build wind kind of where there's red and yellow, you have to decide, am I building it to connect to red or am I building it to connect to yellow? And that's just a choice you have to make. And then maybe sometimes of the year you can make more money on one versus the other. So that's possibly the Texas side of it is tied up in some political considerations. So that's a little bit of a different issue. And then Quebec also has a separate electric grid, which is also connected through DC ties, big DC power lines that bring lots of hydroelectric power from northern Quebec down to load centers in New England and New York. Okay, a little bit about me. I got my bachelor's at Auburn in 2014 and a master's at Illinois, Urbana-Champaign, and my PhD at Texas A&M in 2018. I was working on my PhD with Tom Overby at Illinois, and then my PhD advisor took me into his office in February, my first year of grad school, and said, I'm leaving and moving to another university, and you should come with me. So I did, and I was a little bit scary, but also ended up being a really great experience. I love A&M, I love Texas, and had a great experience there. Worked for a little while for a company called EPRI, the Electric Power Research Institute, in Charlotte, North Carolina, and I was looking on what would happen if an enemy detonated a nuclear weapon high altitude above the U.S. power grid, what the electromagnetic impacts to our system might be. And I'm really interested in power system modeling, synthetic grids, extreme event impacts on power systems. I'll talk about some of these different things. There's a picture of my research group. Also, personal news is I got married last year. So there's my lovely wife, Taylor, and me in St. John, the U.S. Virgin Islands in December. So really glad to be here. I want to also just give you greetings from the Energy and Power Group, Texas A&M. Like Masood said, we have a number of faculty members in power and energy. We've got this control center research facility out in kind of a separate research area about 7 miles from campus. And we also have an IEEE conference every year in February. So if you're looking for a great place to escape the cold and come present some power systems research, come join us in College Station. We'd love to connect with you if you came for that. It's a lot of fun. Usually it's a pretty short turnaround, so you can usually the deadline's around the first week of December. So if you have something that you've been working on in the fall and want to present on there, that's something that we do. And the TPEC conference, by the way, is all graduate student led. Okay, so I want to talk to you a little about synthetic grids because I can't give a presentation without talking a little about synthetic grids. This was a big part of my PhD research. We recognize that we can't test research on the real power grid, at least in the early stages. You can't just run experiments on the real grid. And so we do a lot of our work in simulation and modeling. And therefore, it's important to have really good test cases and simulation cases. And historically, we've had these IEEE test cases, like the 14 bus case that's there. There's distribution ones, there's 118 bus, and a few like that. And those serve well for certain types of initial research efforts. But we're recognizing that more and more of these do not reflect characteristics of the real grid and power system. But then, of course, there are real grid models. There's models of ERCOT, models of the Western Interconnect that the industry are using. And yet, those are difficult to get access to by researchers and by others because they are considered critical energy infrastructure information. And I think there are legitimate national security considerations that make those CEII designations appropriate. Nevertheless, it is difficult for research to get done if there's not the ability to publish your data, publish your results, and cross-validate. And if you can't test your algorithms on realistic cases. And so we did some work to build, basically our goal is to build next generation, newer test cases that are large scale, realistic, and totally public that could be used for geographically based analysis. So here's an example of one. We've been working on this for several years now. We look at our website and download data for lots of different synthetic grids. This is a 7,000 bus model of a Texas synthetic grid. And if you look at the generation layout, you'll probably see it looks pretty realistic. If you know anything about Texas, we've got 4 nuclear units. We've got some coal and gas all over the eastern part of the state. And we've got a significant wind growth. Texas is actually #1 in the country for wind in the western part of the state. And so the generation is realistic, but the transmission network is fictitious. It's totally fake. So it doesn't represent the real grid in this area. And therefore, we're able to put these data sets directly on our website. You can download them and use them. We mainly have transmission now. I'm not sure if I put the distribution one in there. If we did, I'll mention something about that. Could give a whole presentation on the methods for building these synthetic data sets. Basically, what they do is we emulate what happens in real power system planning. We analyze a real power grid. We calculate its engineering performance metrics and also its characteristics from a complex network theory perspective. And we get things like degree distribution, clustering coefficient, and some other geographic and geometric properties. And we reproduce them in these synthetic graphs that we can build through our algorithm and validate them across a suite of validation metrics. Some impacts of those, we've been using them a lot and others have been using them. And here's our website. Definitely encourage you. They're not all that big. Some of them are actually 10 times as big as that, but then we've also got some smaller ones like this. We've got them in a bunch of formats. So definitely want to share the word about that and encourage you guys to be using them if they would be useful for what you're trying to work on. We also have been working on some T&D synthetic grids. So this is, I believe this is the largest power system test case that exists. It's something like 10 million nodes, and it's a full ERCOT transmission and distribution network. And we've got the transmission network in Power World format, and all the distribution is in OpenDSS. It's so big that we haven't even solved it, but we've solved part of it, and we've got a paper that we're trying to get published on that. Basically, what this is we worked with our colleagues at NREL who focused on the distribution side of things. And I don't have to tell you guys that transmission distribution interactions are really important with the way that distributed generation, demand response, EVs, energy storage, and all of that are coming into play. Smart feeders that can reconfigure and things like that. So this is, we're trying to encourage the research community that you no longer can say that larger test cases don't exist or aren't out there. We have them now. They're geographically based. It was really important to us to make them geographically based so that you could connect in with other geographically based information like the weather, like solar eclipses. That wasn't really the main thing, but transportation, for example, you could add a real road network on top of this, for example, and do some studies associated with that. One other thing we did is combine electric and gas grids in 2021. February 2021, Texas had major power outages associated with a winter storm that affected every type of generation in Texas. We even had a nuclear plant that tripped. And one of the big aspects of that was that natural gas pipeline network and the electric grid were not well correlated. And so we have been doing some work to build a test case that maps natural gas and electric together. So here's that. That's available as well. Okay, so getting into one of the main, I wanted to share like some work that we've done recently on power system dynamics and stability. And I want to give some acknowledgements first. Work on the synthetic grids, it's funded by RPE and NSF. We've got some ongoing support from RPE as well. And a lot of this work has been done with help from Tom Overby and some of his team. And a lot of this paper was written by my PhD student, Jongo Beck, who's working on some of these more advanced things as well. Okay, so some of the trends today are changing generation mix. This is a picture I like to show as well. So the renewable energy transition is continuing. We're seeing more wind and solar in the grid. Texas is at the forefront of these challenges. I mentioned Winter Storm Uri earlier with the gas and electric. This is a picture of, so I guess I'll slow down a little bit here. Okay, so the electric grid's 60 hertz. We talked about that at the very beginning. 60 hertz, but actually it's not exactly 60 hertz. It kind of goes up and down throughout the day, and you have control systems that are trying very hard to keep the power system at 60 hertz. Here is a graph of the Winter Storm Uri, February 2021. This is 1:23 in the morning on February 15th, and this is 2:03 in the morning. So this is just a matter of about 40 minutes. And the sort of second white line down is 60 hertz. So that's what the frequency should be. And then you can see the trajectory of the frequency throughout that event. What happens is that if you lose generation, the frequency starts to decline. And so, you know, if you can increase your generation through the control systems, that's the best way to fix the frequency. But if you're in a generation shortage scenario, which is what we were at, then the way to avoid frequency collapse is to shed load. And so that's what was done. There was intentional load shedding. This is an ERCOT picture from the ERCOT report. And you can see that the load shedding that occurred on the red dots, total of 20,000 megawatts of load shed during Winter Storm Uri. But it just kind of goes to show that the frequency control was an important part of understanding what happened in this scenario. And 59.3 is this line right here. That's where under frequency load shedding automatically would have happened. And just missed it by a hair. The minimum frequency was 59.302 hertz. Okay, so grid stability analysis. With all these transitions, stability is at the core of a lot of them. And how do we analyze whether the grid is going back to that idea I was talking about at the beginning, making sure that everything's going to stay synchronized, making sure that the generators aren't going to stay out of sync with each other or get out of sync with each other, make sure the frequency isn't going to get outside of an acceptable range. Also associated with that is controlling the voltage, things that happen in a relatively short time frame over a few seconds to minutes. The typical methods for understanding grid stability are based on time domain simulation methodologies under some predefined conditions. So the electric utilities, they have these detailed time domain models. They will set up the differential equations and they'll integrate them over a long period of time. It's pretty computationally intensive, and they can only do so many scenarios and they can only do it so often. And then they make some conclusions about where stability problems are, stability challenges are. And this has worked well for many years. This is, I think the power system area was actually quite a leader in some of these numerical methods as they were being developed in the eras of computers in the 1960s, 70s, 80s. Really one of the key applications for some of the initial numerical methods. But these are being challenged, and they're being challenged by a number of things. The dynamics of a synchronous machine dominated grid, very different from the dynamics of a inverter based resource type of scenario. And also the variability is pretty significant in the impact of stability. So one example of that would be voltage control in Texas. We've got, like I showed in the previous page, a lot of wind and solar in West Texas. A lot of people live in the East Texas. If you go out here, you're not going to see very many people, but you're going to see lots of wind turbines all over the place. And so there's one of the big issues is transmitting a lot of power across this interface that I indicated kind of nominally with a red line there. And if you take the sum of all of the if you take each individual transmission line, it has a capacity before it overheats, and you sum up all those capacities across this line, you have how much power you could transfer from the west to the east. Okay, that makes sense. Actually, the limit is like 30% of that. It's much lower, and it's much lower because of stability concerns. Stability concerns for controlling the voltage. And you can look at this long-term West Texas export study report that ERCOT put out, where they looked at being able to control the voltage with a large amount of transfer from west to east, and found some limiting factors. Texas's load growth has been so high, with 10 all-time records set in summer of 2023. Okay, going on that. Another issue is short-term frequency response related to inertia. This is an interesting plot that shows every hour of the year for 3 years with the wind penetration on the horizontal axis. You've seen this before, and then the amount of inertia that's connected on the vertical axis. And you can see kind of where the reality is. This is several years old now. And there's some analysis for system-wide. What can we tolerate in terms of inertia? Why is inertia important? It's because it's the short-term frequency control capability of the grid. If you have an immediate imbalance between load and generation, say you lost a big generator, that power has to be made up immediately. And what is that power going to be made up from immediately? Well, right now it's made up from the energy stored in the rotating machines of the synchronous generators, which begin to therefore slow down slightly, which causes the frequency to decline depending on how much inertia you have online. This paradigm is changing. I mean, historically, it's just kind of been ignored because there's been so much inertia, it's been fine. There's several aspects to what this is looking like moving forward. Number one, just looking at how much inertia is okay. And as the inertia goes down, you have sort of like, where is our current floor? And ERCOT said 100 NVA seconds in 2017. That's what they said. I don't know the latest. Another one is saying, is it really just a system-wide inertia, or does it matter where that inertia is located? Much more complicated problem. Not as big a deal in Texas or other parts of the US. Big deal in places like Australia, where you have very weak ties between grids that are interconnected over even much more sparsely populated areas. And then another question is saying, well, wait a second. Do we really need synchronous generation to keep the frequency stable? Or is there something that inverter-based resources, wind, solar, batteries can do to improve frequency control? And that's where you get into grid forming control. Grid forming control is saying that there may be maybe some things that inverter-based resources could do. They actually act much faster than a synchronous machine. And that's kind of like a research area that's ongoing in this. Of course, you have to have energy resources underlying in order to do that. Another issue is oscillations, which is kind of like the counterpart to that other one, which is saying that we have problems with oscillations as the inverter-based resources are being added on. I didn't put it on here, but there's been a number of issues over the last few years where you see something strange about these synchronous generator control systems are relatively straightforward. We know how they operate. And they do have oscillation problems, but people have been studying them for years, and we've got it pretty well taken care of. With wind plants coming on all over the place, and they all have different types of control systems, you see localized oscillations happening back and forth, which is something that even the traditional models can't necessarily predict. And we need more detailed analysis of what they really are doing under the hood. Here's a picture that shows that our synthetic grids, just to kind of give you a sense of what frequency response might look like. Our synthetic grids have dynamic models. So this is a 2000 bus Texas case. And we have dynamic models for all of the generators in this grid. And what I'm going to do is I'm going to show you what would happen if our 2 big nuclear units in the Gulf Coast of Texas were disconnected suddenly, if there was some issue and they had to trip. You're going to have an immediate imbalance between real power, between the generation power and load power. And therefore, you're going to have a frequency decline. The frequency is going to go down. I got a contour of the frequency. White is 60 hertz, pink and red are kind of like just barely going down, and then like blue is like very low. I mean, by very low, I just mean 59.7, but very low in comparison. And you can see kind of how these the frequency goes down and then it's controlled and settles back. But in the meantime, it has some oscillations between the different areas as they go off each other. So this is just kind of another fun video to watch. I like these colorful videos to watch. The event's going to happen at 1 second there. And you can kind of see how the system responds. And this is a stable response. The system ends up coming back to a settled value. The settled value is not 60 hertz, by the way. It's associated with what's known as power system troop control. I'll maybe show it one more time just so you kind of see what an event like this looks like. So you can see the cool thing about this video is you can see like 3 or 4 sort of stability issues kind of all happening at once. Obviously, there's the droop, there's the inertial response, there's the frequency control, there's the settling, and then there's the oscillations. You can kind of see all of that all at once. So I think that's kind of cool to show. So what are some new technologies towards electric grid resilience? Basically, the rest of this talk, which is mostly done, but I wanted to just give you a little taste of some things that we're doing toward a new research effort toward improving grid resilience that we're calling the oscillation flow formulation, which is saying how can we quickly screen a case to figure out how the network topology and the generator models, including IBRs, could potentially create oscillations without having to do the extremely detailed models that take a really long time to run. That's basically the idea of this project. I'm just gonna like zoom through the math, and you can get the slides from me later if you want to study what all of this looks like. But power systems are differential algebraic equations. So you've got some state variables x, and you've got some derivative functions. You've got algebraic variables y with some algebraic functions. You've got a linear network equations. And then you can kind of turn these into a set of real value differential algebraic equations I've got right here. Take the first order Taylor series and assume that each one of these is a base value plus an oscillation at some frequency. So my kind of input parameter is going to be this omega m, this frequency. And I'm going to say, okay, at this frequency, how does the grid behave? And these frequencies I'm going to be considering are like something like 0.1 hertz to like 3, 5 hertz, something like that. I'm going to see like where might we see some. I mean, if you look at back to this video, I won't play it again, but if you remember, this is approximately real time. And so you were seeing some oscillations and they were kind of like in the neighborhood of a few hertz, something like that. So that's kind of what this is looking at. And so we go through this mathematics and we find that we can represent, you can use sort of a phasor notation, which is what we normally use for 60 hertz. And we can say, well, that phasor represents this oscillation. And when we do that, we use the first order Taylor series, we end up with this this sort of linearized representation where this is showing the power system oscillations in each of the variables, and then this is showing the relationship between them. We have, as written, it only has only the trivial solution. Obviously, if nothing's going to disturb the grid, it's not going to have any oscillations. But if we inject a little bit of an oscillation through a basis vector here, then we can solve this with just a single matrix forward back substitution, and boom, we've got an estimate of the oscillations that we're seeing at every variable in the system. So that's kind of the idea here. How well does it work? Here's a 3-bus case that shows this very sparse matrix that we've got, and then basically all I have to do is take this constant matrix and then add a j omega term to all of these diagonal elements, and then solve it over and over for every frequency. And I can get something like this, which shows here's all the different frequencies, and then here's the this is the bus voltage angle oscillations at each of these frequencies, and you can boom, you can see, okay, 1.3, that's the frequency I'm going to see some potential problems in this grid. There's a ton of caveats I could have here, but I'm very encouraged by these results, partly because if you do go to a commercial tool like PowerWorld and you run a full time domain simulation, and then you do a data analysis and you figure out the magnitude and the phase of these oscillations, and then that's the solid line, and the dotted line is the linearized approximation, which takes no time flat, technically speaking. So very fast approximation of that. Here it is for voltage magnitude oscillations, and then here it is looking at, and this one you have to really like think about for a second, but this is the phase of the oscillation. So it's not talking about the voltage phase angle. It's talking about there's an oscillation, and then how is that oscillation offset one from the other. So you can see that the voltage magnitude oscillation, which are the green and blue, they have a phase that stays together, which means that the voltage of the whole system is going up and down together in this oscillation, regardless of the frequency. But you can see that in some of these frequencies, like kind of around where there's significant, that there's actually a phase offset between the voltage angle oscillation in bus 2 and bus 3, and that's kind of indicating that this is like an inter-area mode between those two buses. So that's kind of an interesting thing there. Point is that it really reduced the computation. A few summary thoughts. Still got plenty of time for some questions, but I really think our energy system future is very bright. Lots of challenges in resilience and sustainability, and I really think that electric grid stability is at the core of a lot of that analysis. And I think that our synthetic grids are going to be really helpful for moving forward with that. They're available for your research. We're always looking for feedback to improve them. There's the website again. So thanks for this opportunity to come talk to you. I'm happy to see what is on your mind and answer the questions. Yeah, so thanks.
Thank you. A great presentation. Question, I have another question.
Yes.
One is, with that application show, well, like, make sure we get, what would be the specific application of those things, like in terms of, like, would be like more for planning, or would be more for analyze what happens to drive, or like type of generation, or how would we do those?
So I think there's a lot of reasons why it could be helpful to be able to very quickly figure out what oscillations you might see in the grid. I'm particularly looking at the impact of changing the operating point or changing the topology. So it could be for planning for new transmission lines, could be one of the things, just like a side possibility that just as an example, there's a lot of talk about increasing the topology optimization in sort of market solutions. So in other words, saying not only is our market going to determine what generators are being dispatched, but also might make a decision about, let's take this line out of service so it doesn't get overloaded. But taking that line out of service, right now they don't do that because utilities say, I think, in what is pretty good general wisdom, that more transmission lines makes the grid stronger. But it might be that in some cases you could take out a line and it's not going to hurt anything, but some cases maybe it would. And so some kind of screening methodology that could quickly say, oh, if you do that, look at the oscillations you're going to create. That could be useful. That's one possible application.
So using that type of population can be put into like an optimization program, like you can have it as part of the constraint.
Well, it's more likely to be able to be put into an optimization problem than a full out, numerical integration of the differential equations.
So I guess so those are pretty.
Oh yeah, it's super fast. It's one complex matrix solution. It has limitations though, for sure. I mean, it's assuming a linearized, right, small signal stability analysis as opposed to, so it's not going to tell you much about a big event because the system's quite nonlinear from the perspective of big events, but small signal can be helpful for some. Yes.
I'm curious, I do look at the genetic simulations, they do a lot like this. So when you get it like suppose you brought a solar on quickly or the solar went off or something like that, you've got a oscillation started. Does it tend to stay localized or does it get worse as it propagates? Is it better or worse when it propagates?
Great question. So the oscillating, so there's different types of oscillations. So an oscillation might be caused by something, some control system poorly configured that's messing up. That's a forced oscillation that might be happening. And in that case, it could propagate and you could have, or it would tend to be fairly localized, but then it could cause something else to happen. But what you're really more seeing is you're seeing natural resonances of the network, where the natural resonances, the natural frequencies, which is kind of what I'm looking at here. And so a lot of times we want to look at the damping of those oscillations. And if they're poorly damped or lightly damped, then we might be concerned about something getting worse and blowing up, especially if it interacts with the nonlinearities of the system. But we also have dedicated control systems and power system stabilizers that are intended to damp out those oscillations, but they're mainly focused at the ones we know about, And so if there are ones we don't know about, that could be concerning. Blackout in Victoria.
Canada, when they brought too much solar to the grid, and it got an oscillation going. Not
Not myself.
there's probably not problems. That it would affect it. Resilience would be,
Yeah. Yeah. I mean, so you tend to see the propagation when one thing is causing another thing that's causing another thing. If you have like a frequency that's just bad for the system, something you didn't expect, especially in a highly stressed condition where a lot of the generators are operating at their maximum. I know that in the West, there was this big blackout in 1996 that was related to some oscillations where the whole Western Interconnect basically split into 3 parts, something like that. And so those like California and then Northern mountains and Southern mountains or something like that. And it turned out that there were some oscillations going across the California-Oregon intertie, which is a big transmission corridor there that was loaded more than need to. But you looked at the models, and the models didn't show the oscillations. And of course, modeling has made a lot of improvements since 1996, but still, it's something that you think about. So a lot of times they're local, but then sometimes you can see something happening system-wide, which is bad news.
it's not so much that one thing propagates, but that one thing causes something else, and that goes wrong, causes the next, that's what it's.
I have a question. So the 2021 event in February.
Yeah.
So we can consider it like an extreme weather event, right? It's like it's slow, but it's still considered an extreme weather event. So what's your kind of insight on like how that could be prevented by, and what would have been like the solution or like preventive solutions to prevent from that? And also after that, there was a lot of discussion about like interconnection with the eastern and western interconnection, and how that would have solved the problem. Loaded question.
That's a good question. So, there's how do you handle something like that operationally? And then there's how do you handle something like that in terms of preparation and planning? From an operational point of view, I think I'm pretty safe saying the operators handled the event pretty well. They avoided an uncontrolled blackout. They rotated outages as much as they could. They brought the generation online that they could, and it was a bad event, but you didn't see loss of control of the system. So in terms of stability issues, oscillations, frequency control, and all that, I think the systems did what they should have done. So the problem is that you had an event, an extreme weather event, right? So significant parts of the state, essentially all of the state was in like single digits or lower. Most of the state was experiencing all-time record low temperatures. And so you had every fuel type was affected. And yeah, so another tidbit is that, remember I mentioned those DC interties with the Eastern Interconnect that we have, something like 400 megawatts. The amount of power flowing on those was 0 during the event. And that's because in Arkansas, Kansas, Louisiana, our neighbors, they were all having a similar event, and they didn't have the power available to send to Texas. If you go back historically, what were the reasons for interconnecting, right? It used to be that kind of every state had its own grid and then started interconnecting, growing. What were the main reasons were you buy cheaper power from your neighbors, and your neighbors can help you out in an extreme event and reliability crises. So I think those are still the reasons to interconnect. And but it's not obvious to me whether just being synchronized with the Eastern Interconnect would have been sufficient. Might have helped some. I think there's some talk about maybe adding some more DC ties between ERCOT and the Eastern Interconnect. I think the fundamental solution is better winterization, which has been done. And I mean, in Texas, they tend to design the generators to operate well in heat, right? And so there's a natural opposition between operating well in heat and operating well in cold. And but a lot has been done to increase the weatherization of all the different kinds of generators. And I think that we're not going to see that exact sort of event happen exactly like it did again. But I think to me, the bigger reliability question is, well, what's the next event that you don't know what's going to happen? And that's much harder to predict. Yeah.
Thank you very much for the very nice presentation. When we talk about the significant inertia and power emerging power system.
Like grid forming control?
We talked about also significant inertia coming from solar batteries.
Okay.
And also HVDC connections.
Right.
So, what extent do you think that this synthetic grid can capture these dynamics? When some more power efficiency added, ground.
So how well can the simulation capture the dynamics of the power electronics based resources? We'll see. There's stability modeling, which is what I've been mainly talking about, which is the time step is something like 4 milliseconds, about 4 milliseconds, something like that. It's about a quarter of a hertz, a quarter of a cycle. You know, 240 per second, something like that. And that's good enough for most of the synchronous machine sort of dynamics and the controls and all of that. And depending on the control scheme for wind and solar, it could be good to model some phenomena, but there's also a strong drive to use a more detailed model. The most detailed model that we use in power systems is what's known as electromagnetic transients model, where instead of assuming it's a whole different set of assumptions where your time step can be in microseconds or even smaller. And you know, those, as you might imagine, are much more computationally intense and complicated models, and a lot less standardization for how to run them. But essentially all new wind and solar integration, the utility will have to do an electromagnetic transient solution or integration study, but they will generally do a localized study. So they'll study the plant itself and maybe the substation and some neighbors, rather than I mean, right now, I don't think anybody can or does do like all of Texas with EMT. It's just too hard. Not only hard computationally, but hard from a data and modeling point of view. But I think that's very, very much an open question of like, what are we going to do for modeling stability as the transition continues, and wind and solar are a more significant part of the system dynamics. And so it's a very interesting area to be in. Were there any questions on the Zoom? Yeah.
So regarding the synthetic grid, I just want to make sure I understand how you constructed those. So basically, you had a copy of the real grid, and then you made a fake copy, and then you made sure that they matched in certain parameters, but not matched close enough that they are. Is that right? Or
So the way I like to say it is that they're fiction, but they're good fiction, is one way to say it. So the grids don't contain real grid information at all. So it's not like we took one grid and we tried to make a copy of it. I wouldn't say it that way. We have a lot of real grid models. We've collected statistics on their characteristics from a graph theory perspective, from an engineering perspective, from a geographic perspective. And then we have intended to design the synthetic grids in such a way that they match those properties broadly, but none of the transmission lines match real lines on the grid. And so the synthetic Texas cases match general properties of electric grids, and just by the nature of the geography are going to have some things in common with the real Texas grid, but they're not, you know, trying to reproduce specific problems you might see on the real grid. So I would never say that if you observe something on a synthetic Texas grid, you're gonna see the same thing on the real Texas grid. But I would say that if you develop an algorithm that is capable of running and solving and simulating on one of our synthetic grids, there's a good chance it's getting close to being ready to run on a real one, even if you don't have access to it. So the main advantages are for testing, demonstration, giving presentations, publishing, cross-validation, software development.
Okay, and so you could develop a synthetic grid for a location without having like a full complete.
Oh, sure, and we have,
Yeah.
yeah. I mean, I don't have a Hawaii grid, I've done a Hawaii.
Okay.
So great. So other questions? Thank you for visiting us.
Absolutely. Thanks for your attention.
Thank you.